All right. You guys want to wish anything to Lexi there?
We love you, Lexi.
White cash.
Or whatever. Okay. So anyhow, 3.8 is called Newton's method. Newton's method. Newton's method. All right, I don't know about you. I saw the title and thought, oh no, Newton's method. Newton's super smart dude, right? Way too intelligent for our pay grade. So we're in trouble, Newton's method. Thankfully, we don't have to come up with a method like Newton did. We just need to figure out how to use it. All right, and so that's the idea. So a little context. A couple days ago, Kirsten came to me over the problems that we were doing where we were looking to sketch the graph, right? And if you remember to sketch the graph, there were a whole bunch of things that we were looking to find to be able to sketch the graph. And, you know, limits and asymptotes and extrema and points of inflection, but then also zeros, right? Y-intercepts, no problem, but zeros of the function. And, you know, anything linear, you don't need to write this, I'm just getting the context. Anything linear, we can find the zero to that, no problem. Very, very simplistic, very, very easy. Anything quadratic, just give that one as an example, we can find the zeros to that as well. Because when it's quadratic, we have three methods to get to those zeros, and that is we can, if possible, take the square root of both sides. This one fits that category. We'd get to zeros. Or we can factor and set factors equal to 0 and get to zeros. And if it doesn't factor, we can use the quadratic equation. So the quadratic equation is going to allow us to find the zeros even when we can't factor the polynomial, which is great. Now we're able to get to zeros. Well, what happens when you get something of greater degree that doesn't factor? Because right now, the only methodology we have at finding those zeros is to factor it. And therefore, then we can factor it and then set it equal to 0 and find the zeros. But if we can't factor it, we're not going to be able to find those zeros. And they may exist, but we can't find them. So how are we going to do that? Answer, Newton's method. So Newton's method is a method to find the zeros. So number one, use to find zeros when algebraic or when algebra techniques won't find them. To find, I'm going to put in green zeros, which again are what? X-intercepts. To find zeros when algebra techniques won't find them. Find zeros when algebra techniques won't find them. Okay, so that's the idea. Let me see if I can help you to understand the concept. So that's the use, here's the concept. So we're just going to make a sketch for our notes so we can refer back to the sketch later on. So we got just a simplistic Cartesian plane here. And I'm going to take my black, and this doesn't have to look perfectly, but just some curve like that. And I would hope that you would agree that that value right there is indeed the y, or the x-intercept, the 0, right? And so what we're after is that point. And how in the world are we going to find it? Well, here's the concept. Here's Newton's method. Let's take a point. I'm going to put it right there. And we'll call it x sub 1. So that's the x-coordinate of that point. And that point is a point that's tangent to the curve. And therefore, then we get this tangent line. And if you were to look at the coordinates of that point, that tangent point, it would be x sub 1 comma f of x sub 1, right? Okay, no big deal. And what this point would be right here is x sub 2. All right, so at first look, we're going to have a value here, and we can find a value here. And this value needs to correspond to C. Well, it's a bit of ways from C. And truly it is. But what you want to do is, after x sub 2, you want to find an x sub 3, which will be closer to C. And guess what? After you do an x sub 3, you'll do an x sub 4, which will be even closer to C. Until eventually we get to C. And this is the idea, and this is the concept, and this is what's called Newton's method. And we'll write this in a moment, but these are called iterations. Each successive attempt is an iteration. And we'll get closer and closer and closer and closer to C by running the next iteration using the formula that's called Newton's method. So that's the concept and that's the idea. And so closer and closer and closer to where we're so close to C that we're literally close enough for our purposes to get that value of C. All right, so that's the idea, that's the concept. So what's that formula? So here's the way they write it. X equals x sub 1 minus f of x sub 1 divided by f prime of x sub 1. All right, so there's calculus now. We've got a derivative involved, right? And to me, you keep going down the road. So then next down the road is, I don't even want to write that one, this one. So x sub 2 is going to be x sub 1 minus f of x sub 1 divided by f prime of x sub 1. I like this look better to my brain. This makes sense. And I'll try to show you what I mean in the future. But I'll give you the next iteration. So x sub 3 would be x sub 2 minus f of x sub 2 divided by f prime of x sub 2. And et cetera, et cetera, et cetera. Down the road you go in these iterations. And so then we'll write here, each successive application is called an iteration. Each successive application or use of the method, right? Application is called an iteration. Generally, it's going to take like 3 to 4 iterations to get to where you want to be. 3 to 4. And when do you stop? You stop when reaching the desired accuracy. Stop when reaching the desired accuracy. Stop when reaching the desired accuracy. You might say, well, what is that? Most problems will tell you. Again, we're working problems. In real life, you would be the one determining how accurate you want to get. Obviously, if you're trying to go to Pluto, I would be quite accurate. You know, if it's not that big of a deal, then you don't have to be as accurate. But that's the idea, and you'll have problems, and I'll tell you that. All right, so let's do number 3, an example. Let's see, how much space do you want for this? At least half a page. It's my recommendation, and you're gonna have to get your calculator out, because I got to tell you, with the example, I probably calculated it. Oh, I hate to admit this. I'll just say multiple times before finally getting the numbers down in the right place with the right signs to make the numbers work. So here's the question. Use Newton's method. Use Newton's method. Use Newton's method to approximate the zeros. To approximate the zeros of, here's our function, f of x equals 2x cubed plus x squared minus x plus 1 to within, I'm going w/I, because without is w/O, right? So within has to be w/I, right? I mean, has to be. To within 0.0001. That's pretty accurate, right? It's pretty accurate. All right. How do you start these? Well, we've got a conundrum. Here's the conundrum. Let me go back to this. All right. If we had a scale, don't do this on your original, but if we put a scale here like 1, 2, 3, 4, our x of 1 would be what? Like maybe 1.6? Make sense? Let's use 1.6 for x sub 1, right? The value of this tangent point, right? Come on. So, what is missing? There's no graph. We don't have a graph. Yeah, I know. Punch it in your calculator. Yes, I understand. Use Desmos. Yes, I understand. It's not the idea. So we need a rough sketch. Now, we are not going to do what we did in, 3.6. And because we're doing all this just to get to 0, so we're going to do a rough sketch. Rough sketch. Rough sketch. So first off, in our rough sketch, let's figure out the end behavior. That should be simple. That's right, 3 seconds. So end behavior. Oh, come on, green. So the -2 says it's going to, or the +2 says it's going to end up which way? End up. And the 3